our discussion series in solutions. In this video, we will be discussing concentration and dilution. When we say concentration of a solution, it is given by the quantity of solute present in a given quantity of solution. It is an intensive property which does not depend on the quantity of the mixture. And concentration also tells us how much solute is dissolved in a given amount of solution. Presented here are the different terms and formula of concentration. So let's have some examples or sample problems. The first one is to find the concentration of calcium in parts per million in a 3.50 grams pill that contains 40.5 milligrams of calcium. So to solve this problem, we have to convert milligrams to grams first by using this conversion factor, and then find the mass ratio of calcium to pill and multiply by 10 raised to 6. So if we do it this way, we will arrive at an answer 1.16 times 10 raised to 4 parts per million calcium ion. The next example would be the label on a 0.750 liter bottle of Italian Chianti indicates 11.5% alcohol by volume. How many liters of alcohol does the wine contain? To solve this example, we know already that the volume percent of the alcohol and the total volume, so we can find the volume of the alcohol. So we can use the formula we presented earlier. In that case, we multiply the 0.750 liter Chianti by 11.5 liters alcohol per 100 liters of Chianti. Remember that this is the concentration of the Italian Chianti. And then after that, we will arrive at the answer 0.0862 liters of alcohol. And then for the next example, a sample of rubbing alcohol contains 142 grams of isopropyl alcohol and 58 grams of water. What are the mole fractions of alcohol and water? So before we compute for the mole fractions of alcohol and water, we have to convert the grams of solute and solvent to moles in order to convert them or to calculate the mole fractions. So we recall from General Chemistry 1 our lesson on mole conversions, wherein we multiply the mass of the substance by the conversion factor 1 mole over the molar mass of the substance, which is 60.09 grams in the case of alcohol. And we will arrive at the answer 2.36 moles of isopropyl alcohol. While in water, we multiply 58 grams, the mass of the compound, to the conversion factor 1 mole over the molar mass of water, which is 18.02 grams. And then we will arrive at the answer 3.22 moles of water. Now, following the formula we presented earlier, to find out the mole fraction of each compound, so we divide the moles or the amount of the substance or amount of the solute or solvent by the total amount of solute and solvent added together. So to find out the mole fraction of isopropyl alcohol, we divide 2.36 moles of isopropyl alcohol by 2.36 moles of isopropyl alcohol and 3.22 moles of water. So we will arrive at the mole fraction 0.423 for isopropyl alcohol. And then in terms of water, for the mole fraction of water, we divide 3.22 moles of water by 2.36 moles of isopropyl alcohol plus 3.22 moles of water, and then we will arrive at the mole fraction of water 0.577. That's how we solve the mole fraction. Now, in terms of molarity of the solution, here is a sample problem. What is the molarity of an aqueous solution that contains 0.715 moles of glycine in 495 ml? So to solve this one, we have to remember that molarity is the number of moles of solute per liter of solution. That's why given 0.715 moles of glycine per 495 milliliters of solution, we have to convert milliliters to liters by using the conversion factor 1000 ml over 1 liter. And then we will solve the problem. So 0.715 moles of glycine over 0.495 liters will be equal to 1.44 molar glycine. Remember that the formula for molarity is moles or amount of the solution or amount of the solute over liters of solution. So in terms of this one, the amount of solute is 0.715 moles of glycine, and then we have 495 milliliters or 0.495 liters of solution. And then we can also calculate the mass of solute in a given volume of solution. Example here, how many grams of solute are in 1.75 liters of 0.460 molar sodium monohydrogen phosphate buffer solution? So to solve this problem, we have to calculate the moles of solute using the given molarity and volume. We have to manipulate the formula for molarity and then convert moles to mass using the molar mass of the solute. So in this case, we have 1.75 times 0.460 moles over 1 liter. So you might be wondering, where did this come from? Itong 0.460 moles over 1 liter. Remember that based from the problem, the solution is 0.460 molar. And the unit or the expanded unit for molar is moles per liter. So we can assume that from this solution, there is 0.460 moles in 1 liter of solution. So we perform this operation and we arrive at the answer 0.805 moles of sodium monohydrogen phosphate. But since the problem is asking how many grams, you have to convert this amount of substance in moles to grams by multiplying it to the conversion factor. 1 mole is equal to the molar mass of the substance. In this case, we have 141.96 grams of sodium monohydrogen phosphate is equal to 1 mole of the particular substance. And then we will arrive at the answer 114 grams of sodium monohydrogen phosphate. And then here is how we prepare solutions in the laboratory. So using again a volumetric flask to make a standard solution of known concentration, we add the weighted amount of solute in the volumetric flask, and then we add distilled water about half of the final volume, and then after that we cap the volumetric flask and shake to dissolve the solute completely, and then add another distilled water to volume marker until this calibration mark. So the solution process may be exothermic, that releases heat, and this may cause the liquid to show a larger volume than is real. Allow the solution to return to ambient temperature and check volume again. So that is how solutions are prepared in the laboratory. Now, if we look at the other terms of concentration, we also have molality. So molality, here is an example. What is the molality of a solution prepared by dissolving 32 grams of calcium chloride in 271 grams of water? So in this case, our plan is to divide the moles of solute by the kilograms of solvent. So we still need to convert 271 grams to kilograms, and then divide by the mass of water, being sure to convert from grams to kilograms. And then we have another term for concentration, which is molality. So in here we have an example. What is the molality of a solution prepared by dissolving 32 grams of calcium chloride in 271 grams of water? So remember that molarity is defined as moles of solute divided by the kilograms of solvent. So we have to convert the mass of calcium chloride to moles using the molar mass, and then divide by the mass of water, being sure, or do not forget, to convert the mass of water to kilograms, from grams to kilograms. So in here, from the mass of the solute, which is 32 grams, we have to convert it to moles by using the conversion factor 1 mole over 110.98 grams of calcium chloride, which is the molar mass for the compound. So we will arrive at the answer 0.288 moles of calcium chloride. And then to compute for the molality, remember that you have to convert 271 grams of water to kilograms, which is indicated here. And then we divide the amount of substance, 0.288 moles, by 0.271 kilograms, and we will arrive at the answer, 1.06 molal calcium chloride. And that's how we solve molality. Now, there are cases wherein sometimes a solution has a higher concentration than is needed. Therefore, dilution is needed. When we say dilution, it is the addition of solvent to decrease the concentration of a solute. So the solution volume changes, but the amount of solute remains constant. So for example, a stock solution of a drug is often supplied in a concentrated form to take up less space on a pharmacy shelf, and then it is diluted so that it can be administered in a reasonable volume and lower concentration that allows for more accurate dosing. As I have said earlier, a key fact to keep in mind that the amount of solute is constant. Only the volume of the solution is changed by adding solvent. So how do we solve for dilution? We have the formula M1V1 is equal to M2V2. Let's work on some examples. Isotonic saline is a 0.15 molar aqueous solution of sodium chloride. How would you prepare 0.80 liters of isotonic saline from 6.0 molar stock solution? So to solve this problem, we have to dilute the concentrated solution. We add only the solvent, so the moles of solute are the same in both solutions. Remember that. And then the volume and molarity of the dilute solutions give us the moles of solute. Then we calculate the volume of concentrated solution that contains the same number of moles. So if we work around the problem, we have to use the volume and molarity of the dilute solution. So you have 0.80 liters of solution, multiply it by 0.15 moles of sodium chloride per 1 liter of solution. So this is the concentration of the dilute solution. And then we will arrive at the answer, 0.12 moles of sodium chloride. So using the moles of solute and molarity of the concentrated solution, we have here 0.12 moles sodium chloride multiplied by 1 liter of solution over 6.0 moles of sodium chloride. We will have 0.020 liters of solution. Therefore, a 0.02 liter portion of the concentrated solution must be diluted to a final volume of 0.8 liters. And then we have solution stoichiometry. So this will be the combination of what we have been discussing for parts 1 and 2 of this discussion series, and then the stoichiometry that we discussed in General Chemistry 1. So we have here sample problems. A 0.10 molar hydrochloric acid solution is used to stimulate the acid concentration of the stomach. Now, how many liters of stomach acid react with a tablet containing 0.10 grams of magnesium hydroxide? Remember that in our stoichiometry discussion in General Chemistry 1, we have to write first a balanced equation of the reaction. You have to write first the balanced equation of the reaction. So we have here 1 mole of magnesium hydroxide and 2 moles of hydrochloric acid will form 1 mole of magnesium chloride and 2 moles of water. And also in this case, we have to convert the mass of magnesium hydroxide to moles using the conversion factor. 1 mole of magnesium hydroxide is equal to 58.33 grams of magnesium hydroxide. And then we will arrive at the amount of a substance, 1.7 times 10 raised to negative 3 moles of magnesium hydroxide. Afterwards, we use the mole ratio from the balanced equation to determine the moles of hydrochloric acid. And in here, we have the ratio 2 moles of hydrochloric acid is to 1 mole of magnesium hydroxide. So if we perform this calculation, we will arrive at the answer 3.4 times 10 raised to negative 3 moles of hydrochloric acid. Now, we have to convert the volume using molarity. Remember that the problem is asking about the liters of stomach acid to react. So in this case, we convert this to 3.4. We convert 3.4 times 10 raised to negative 3 moles of hydrochloric acid to liters of solution by multiplying it with the molarity of the compound or the substance, which is 0.10 molar. So we will multiply 3.4 times 10 raised to negative 3 moles by 1 liter hydrochloric acid over 0.10 moles of hydrochloric acid. And then we will arrive at the answer, 3.4 times 10 raised to negative 2 liters of hydrochloric acid. So in acid-base titrations, a burette is used to deliver measured volumes of an acid or base solution of known titration to a flask that contains a solution of a base or an acid, respectively, of unknown concentration. So if the concentration of the titrant is unknown or is known, then the concentration of the unknown can be determined. Plotting the pH changes that occur during an acid-base titration against the amount of acid or base added produces a titration curve. By the way, this is a titration setup in the laboratory. And then, the shape of the curve provides important information about what is occurring in solution during the titration. Before addition of any strong base, the initial hydronium ion concentration equals the concentration of the strong acid. We will discuss more of this when we go to our acids and bases module. And that's it for our second video in the discussion series. Thank you for listening.